this molecule, can you draw the Western structure? Then you gotta think about, okay, what is gonna move, right? Always a double bonds or multiple bonds like this one or negative charges. So I say, what about the oxygen negatively charged on this side, nitro groups? And then once that comes in, you're gonna make a nitrogen oxygen double bonds. That's gonna make a nitrogen 10 bond, 10 electrons. So something gotta go up. So this one going up, that looks like almost like a carboxylate instead of the nitrogen groups. But there's another thing you can do. What is the other one is this double bond, it can come in this way, making a double bond with the carbon with the nitrogens. That makes a nitrogen with 10 electrons, so you gotta give up. Thankfully, there's double bond here. So this double bond go to the oxygens. Then you get two oxygen, both of them negatively charged. And then not only that, this carbon becomes a positive charge. So it's a lot of electron can be moved around. It looks like invalid, but this is invalid because we didn't make anything wrong. These are valid resonance structures. So sometimes you've got to be really think about every possibility. Among these things, which was the major contributors, minor contributors, those two have the same stability, those two are major. This is going to be minor. It's because of this carbon doesn't have enough. But what about we going the other way? If electron pairs are coming in this way, it pops out. It's kind of this question we talked about, which direction electron going to go, right? It goes this way, in this case. If you move it the other way, this looks very similar to this one, except now the carbons are negatively charged, which is not a problem, but you're going to make the oxygen positive charges. It's the same thing. You drop the ball on Earth, it doesn't float up, it goes down, right? So that's kind of the reason why these are invalid resonance structures. All right, can you draw the resonance structure with this one? This is a really significant question that people have answered long time ago, because that makes understanding of the natural products something for the protein. That molecule having a carbon oxygen double bond here. That can only make a resonance structure, this one going up here, but that we talked about minor contributors. But this one, nitrogens, but even though I didn't show the lone pair there, you should imagine lone pairs on nitrogens, right? That lone pair of the nitrogens, that's the one that actually participate with the resonance structure of the carbonyl. That resonance electron pairs coming in, making a carbon nitrogen double bonds, which you cannot do that alone. You have to make this double bond goes to the oxygens, make the oxygen negatively charged. It's got to be synchronized movement here, but that way you can draw the resonance structure. But these resonance structures are much more significant compared to we draw the resonance structure from that one alone. Why? Because this nitrogen now having a double bond with the carbon, now the single bond shown like this, resonance structures makes it look like a double bond. And that's what makes it significant. We'll discuss later. But this is a very significant resonance structures. Yet, it is still the minor contributors. Right? Because, octets are all filled here, octets are all filled there, but the difference between these two, we got charge separation here, but this one does not. So it's still the major contributors, but minor contributors signify why these bonds are so stable. You don't understand what their bond is. Their bond is basically the amino acid comes together, make a protein. They making this bond. The beads of the amino acid put together, they make a strings, and then that is a so strong bond. That's why proteins are so difficult to digest. Of course, you do it in the stomach very easily, but chemically it's very difficult. But anyway, so we'll talk about more later. But that is kind of what things we want to recognize. We want you to recognize later.